Hello and welcome to session 290 in the AISafety.com reading group. Tonight we'll be discussing the article Counting Arguments Provide No Evidence for AI Doom by Nora Belrose and Quentin Pope. Nora Belrose and Quentin Pope are together the majority of the AI optimists that blog at the AIoptimist.com, I think. We've discussed their work previously, and we will also be talking quite a bit about Joe Carlsmith from Open Philanthropy. This is a post that is just very new, just a couple of weeks, posted in all the regular places, and on the meta level, it has this the name "No Evidence" as part of the title, and the statement that this provides no evidence is often considered a red flag here by Scott Alexander, for instance. And I think in particular I would caution about using this kind of very confident language. In particular, Quentin Pope has previously argued that Eliezer Yudkowsky is overconfident, and in this case just arguing that it is literally no evidence, that there's no chance that Joe Carlsmith is right, is a really high bar. And I think in this really difficult area, I think we should be wary of this kind of overconfidence. But that was just a meta note. In general, I am really happy about this kind of skepticism, and I think in particular it stands out in contrast to some of the earlier criticism we've seen, not just from these people but also from others. For instance, 20 sessions ago we read Quentin Pope's My Objections to Eliezer Yudkowsky, where we went through all his disagreements with his list of lethalities, and this was a post that was really highly upvoted, but had really poor discussion. Unfortunately, it was kind of badly received on for responses. And my analysis of the theory was that many AI skepticists probably feel that many points in Eliezer's lists are wrong, and that and if you want to respond to all of them, then the only way to do that is necessarily to make it very shallow. And the people who respond, then they do that with like hot takes and saying things that are kind of irrelevant, and that makes it hard to get in kind of productive discussion going, either for Quentin and also for the other people, so we don't get this actual synthesis out of a broad criticism. And back then I encouraged him to focus on like a single point, preferably one of the ones that were like flagged as central. And we almost get that here. We get a thorough counter-argument to a single argument. In this case, an argument by Joe Carlsmith. I don't think actually either Eliezer Yudkowsky or Bostrom have used these arguments, but like they've written a lot, and I'm only like 30% sure. It's certainly possible they have. But my point here is this is a lot better. A thorough counter-argument to a single point, even if you can just find a single line in Bostrom's book Superintelligence that you believe is wrong, and that you can comprehensively argue for that, is much more likely to give good discussion compared to just some superficial criticism. And also Joseph Carlsmith has responded very positively to this, and I think many people do in fact appreciate this. To start with, Joe Carlsmith's argument for AI Doom. And this is a paper he's written as part of Open Philanthropy called Scheming AIs. Will AIs fake alignment during training in order to get power? It's 120 pages, which is quite a bit actually compared to how relatively simple the argument is. And Nora Belrose in this work wants to debunk the counting argument, which is a central reason to think AIs might become schemers. And I am like Joe Carlsmith actually doesn't really think this is that central. He puts 25 probability on AI Doom, and he starts by introducing this as an example of an argument, but he doesn't endorse it. He says arguments close to that may be more correct, but there is a specific one he calls the hazy counting argument that he gives more weight to, but like this is a very small part of his probability mass in total. He's much more focused on like empirical investigations and things like that. He seems to care much more about that, and I think that's a reasonable thing. And I when I learned about this, like I was like, okay, why not focus on his actual arguments? And in particular, I was also a bit annoyed that when Nora Belrose introduced the counting arguments, it doesn't really make it clear that this is not one that Joe Carlsmith really truly considers central or even endorses. And so, with regards to empirical work, like everybody seems to agree that empirical work is more important. In particular, the specific kind of empirical work that would really have a bearing on this would be the work done by Ivan Hubinger, for instance. And this is the kind of thing that if it kind of sounds like Nora Belrose has empirical arguments against this, and that is really the thing that I think people ought to talk about in order to really make progress. But if you want a theoretical, all the way back to the Prior's discussion, then we have one here, and I've tried to talk about it here under the heading "The Principle of Indifference as Applied to a Neural Network." So, let's talk first about uninformative priors. Like, you have a situation where you don't know anything, what should your prior be? Like, you have a variable or something, and if you don't have any information, what should your prior be? And in the first couple of examples, we're going to think about a neural network, in particular in the beginning, the weights of a neural network. If you don't know anything about that, what are the weights going to be? And what's the network going to do? Well, in general, this is kind of hard to reason about because non-informative priors are kind of rare. We always, in practice, have some ways to gain information that will help us, except in really, really contrived situations. But there are 3 places where it could in fact be useful. It could be useful if we're speculating about some experiments that we can't run yet. Like, for instance, if you train a superintelligence, what will happen? You need to have some kind of prior on this, and if you believe this is a sufficiently strange area, then an uninformative prior may be a good idea. If you are speculating about facts that are deliberately hidden from you, then sometimes such a prior could be useful. Like, is a particular agent a traitor or something like that? Is something you can't immediately see. Or if you have a mathematical statement, you don't know if it's true, maybe you haven't even formalized it yet, then some kind of prior would be useful. For instance, in this case, the actual claim that we are interested in is a particular AGI aligned or not. So sometimes we can maybe get some information, get some usage out of at least figuring out where to start, and that may be with an uninformative prior. Here is an experiment with 12 different outcomes, labeled 2 to 12 and all else. And what should be our initial prior on this? We could use the principle of indifference. That says that if we don't have any evidence, we should just distribute our probability mass equally along these 12 possibilities. And that seems like a reasonable prior, and we could then do some experiments. In this case, the probabilities actually come from throwing 2 die, and in this case we end up with this. And like, if we didn't know it came from 2 die, then I think it's a reasonable prior. In this kind of situation, the principle of indifference does work quite well. And the same if we go to a neural network. If you initialize it randomly, then you know what are the weights going to be. There's probably like 1 in 10 of them are going to be between 0 and 0.1 or something like that. Of course, in practice you use He initialization for the weights or something like that. But like, the principle is in fact pretty sound for estimating what are the weights going to be. So when is this principle not sound? Well, let's consider that I make a prediction based on this principle of indifference. Like, I have an experiment, like a die, and I say there's a 1 in 6 chance it will be a 6. And a lot of people say, seems like a good prediction, the best prediction you can make in this situation. I think this seems right. And then it turns out the die is based, and the call was bad. Does that mean that the principle of indifference was bad? It led us to some poor predictions, but I think, in fact, in this case, I would argue that the principle of indifference still performed quite well. Just because it performed badly in one specific case doesn't mean that the principle is unsound. But of course, these were 2 easy examples, both where you have the neural networks that were just straight random, and the limited number of outcomes in the with the dice. Let's try to find some more difficult examples for figuring out how valid the principle of indifference are. And for that, we are going to look at the neural network when we do stochastic gradient descent. So the very first thing I did back in 2005 with neural networks was to build one that did optical character recognition, like looking at the pixels and trying to figure out, is this an A, B, C, etc. So this is like a very standard example in my mind. So probably when you start out with random weights, then if you try to see can it do optical character recognition, it probably can't. And if you do stochastic gradient descent with some good training data, then after a while it will be able to find its way down the landscape to a low loss, and eventually it will be able to. That's like the standard story about how stochastic gradient descent works, right? The question here is, before you started, I claimed before that if you do 0 iteration of stochastic gradient descent, then probably it doesn't work. Like, you have to actually do this, but how can I be so sure actually? And the way I would do that is to deploy a counting argument, because if we look at the space of all neural networks, then there are more neural networks that don't work, that don't do optical character recognition, than there are of neural networks that do recognize characters. And based on that, I assume that if I don't do stochastic gradient descent, it doesn't work. I'm really sure of this. I haven't even tried to formalize this. I don't think I can easily formalize, but I have a really, really strong idea that if you don't train the network at all and just start with a random initialized network, you're not going to get something that works the first time. So here it worked. And then let's take another example. Let's say you do some clustering on the characters, and you put them into 26 clusters, and maybe if you have one particular, let's say number 16, does that correspond to W? What is the probability after you've done that? Well, the principle of indifference says 1 in 26. There's no reason to privilege that it will be number 16 that's W, so probably 1 in 26. And here again, the counting arguments work just fine. Okay, let's take another question. The weights, what is the probability that all the weights will be linear combinations of the initial weights after you do a stochastic gradient descent? Well, in this case, most random numbers don't satisfy this at all. So this seems a priori extremely unlikely if you don't know anything about stochastic gradient descent. But actually the way stochastic gradient descent is that after each iteration, there are still a linear combination of the previous weights. So it does in fact respect this invariant. And that means that the counting arguments in this case actually fail. Even though very, very few random numbers have this property, the ones that stochastic gradients selects are not random, but chosen according to an algorithm that has this property, and so the counting argument fails. So the question from here is, counting arguments seem to, like, we've given 3 examples, one where it really obviously worked, where it kind of works, and one where it fails. And it kind of depends on the bias arguments. Here we have a really strong bias argument for SG stochastic gradient descent finds a very specific kind of solution that satisfies this. And up here we have like strong reasons to expect that most neural networks don't do optical character recognition. So this kind of bias argument is the one that can truly make or break the counting arguments. If you have strong arguments, then this prior doesn't matter. That's kind of the thing with priors, that if you start with a prior and then you like get good arguments and evidence, and then the prior doesn't really matter. The indifference principle does have potential flaws. Sometimes it gives really wrong predictions, and that's of course a problem. You can in fact give some examples where it gives like different paradoxical examples. Here's one where a classic example where depending on how you split the outcome space, you get different conclusions out of it. And even just naming this, the principle of indifference, is something that Joe Carlsmith does not do. He does not use this term, and so he doesn't discover the classic counterarguments to this. And I think Nora Belrose deserves epistemic points for figuring out that this is like the standard term. Michael Huemer, the philosopher, claims in a book that I don't have access to that the dominant view is that this principle of indifference is just straight up false. I'm somewhat confused about this claim, because like if you need to assign some probabilities, right? And if you don't know anything, then like what probability should you assign? I think some explanation here would be nice, and also some kind of explanation why Michael Huemer is the right person to ask about this. But I think my overall conclusion about the indifference principle is that, in fact, in many ways, in many situations, the indifference principle is in fact pretty sound once we have, depending on what kind of other bias arguments we do have. There is some kind of intuition behind that there are more things that are not apples than there are things that are apples. This kind of intuition is probably reasonably sound. Now let's count a particular thing. We are going to count schemas. So this is Joe Carlsmith's argument. So stochastic gradient descent somehow selects a model that has high reward. And we're not really going to talk about how. He does that later in this 120 pages, but not here. He just says we get a model that has high reward. What kind of model is it? He identifies 4 model classes that all get high reward in training. The first is what he calls training saints. So this is the thing that we actually want. An agent that like values the thing we want. Then we have misgeneralized non-training gamers pursuing a high reward goal. Someone who seeks reward on the episode, and finally schemas. So the first ones, the training saints, they need to actually value the thing that we are interested in. Someone who misgeneralized the goal. So like the example I'm using here is fool's gold. You're training the algorithm to find gold, and then actually it turns out to look for fool's gold. Then that must be something that really looks a lot like gold to some extent. Reward on the episode seekers are agents that terminally value just getting reward on the episode. And finally, schemas can basically value anything else, because a schema will just pretend to be aligned and actually value something else. So training saints, they need to hit a rather narrow goal, because if it's a really, really easy goal, then we possibly wouldn't even use AI, or there may be other reasons to think that training saints are relatively rare. For misgeneralization, like you can sometimes find some things, but as the training gets better in general, it becomes harder and harder to find good examples of this. Reward on the episode is like literally a single goal, and that seems to leave quite a lot of space for everything else. And perhaps a supermajority of the models that are available for SGG to select are schemas. And this forms the basis of the counting argument. Basically, there are more schemas that perform well in training, so other things equal, we should expect stochastic gradient descent to select a schema. And of course, the key thing here is in this other things equal. And that's these bias arguments that we talked about. And Carlsmith, indeed, over these 120 pages, points out a lot of potential problems with this argument, and talks a lot of this, like what are the actual properties of the stochastic gradient descent, and what are the properties of these models that get high reward, and things like that. And Nora Belrose chooses to attack a somewhat surprising place. She objects to the structure of the argument, and she does that by making a structural identical argument for a false conclusion. Let's have a look at Nora Belrose's counterargument. This is a simple image of like overfitting. You are trying to like distinguish between red and blue, and you do that here with a good generalization, and then also a kind of an overfitting line here. And we in the same argument, stochastic gradient descent selects a model that fits the training data well, and there are two kind of classes that fit the training data. There is the models that have a function that generalizes, and the models that just overfit. So these are the two classes that both like get high reward in that sense. And something that generalizes needs to be fairly specific, whereas the models that overfit on the training data, on unseen data points, they are not constrained in any meaningful way, so they can be much more things. So in that sense, there are more overfitters that perform well in training than there are like balanced generalizers. So other things equal, we should expect stochastic gradient descent to select an overfitter. And I accept these arguments are structurally similar, but the difference is of course in the words other things being equal, because other things are totally not equal in how SGD selects. And this is an attempt at a reductio argument that this is an absurd conclusion, and so we should abandon some of the propositions. And I think I'm not willing to call this absurd. I think the principle of indifference here caused us to select something that was wrong, but I don't think it caused us to predict something that was absurd, in particular because many smart people thought that neural networks would overfit if they had more parameters than training data. Now let's talk about realism and reductionism. So this is like a classic example. There are some apples that that some observers see, and they make a model of this, and do these apples really exist, and does mathematics really exist? This kind of realism and reductionism are like two things that are often employed in discussion about like God or free will. If you're realistic about free will, then you believe that free will really exists, and free will is mostly like what you think it is. And if you're a reductionist about free will, then you explain free will in terms of like brain structures and everything else. And talking about this is some kind of error, and you should just taboo it. And this is like the reductionist view on a particular topic. So in general, I think I prefer reductionist thinking for like things like free will and God, but I don't think that realism and reductionism are that much in opposed to each other. Like I feel the important thing is if you're explaining a concept or if you're explaining away a concept. Like if are you explaining God in some way that gives you prediction about gods, or are you explaining away God by saying, oh, it's just Spinoza's God or something like that? Like for instance, my car has an engine is a statement that like is inside my mental model. It doesn't reduce to cylinders and valves, and I can like talk about this, communicate with other people, and like this is a belief that pays rent to me, and so that is why I'm a car engine realist, even if I'm a reductionist about many other things. So now we are going to deploy this by talking about goals. Goal realism versus goal reductionism. So in goal realism, you think of a model that could have a goal slot and a goal achieving engine, and then because there is truly a goal there, then you can just replace the goal in the goal slot, and then the engine will just pursue the new goal directly. Whereas a goal reductionist view would say that goals are just patterns of behavior that are contextual heuristics that work in practice, but there is no true goal that the system has in this say. And Nora Belrose has this picture that explains this. I'm not entirely sure this explains that much, but I've reproduced it here. So my this seems much more like an empirical question than it seems a philosophical question, because you can totally build an optimization engine that has a goal slot, and like that seems like a thing you can totally build, and you can also totally build one that doesn't have any meaningful goal and just have a bunch of heuristics. And in particular, like back in my day, we did good old-fashioned AI, and back then the strong idea was that we would in fact have a very explicit utility function / goal slot, and like this was totally the way to think about it. And that obviously also biases me to think about AIs mostly in this very explicit we design the utility function view. So I think what's going on here is that we're kind of mixing three questions. There is about for goals, is goal realism or goal reductionism the more sound philosophical concepts. Which of these two does the LLMs that we look at right now have? And how about humans? Do humans actually truly have goals, or is human behavior better explained in terms of our heuristics? So for the second question, which I think is most interesting, would stochastic gradient descent make something that has goal slots? And it is claimed that empirically, trying to have a separate goal slot cause worse performance. And well, whether that is true or not is a question, but we truly want our AIs to have a goal slot, so we can like build the AI and then point it towards something and say, go do that, and then have it a goal slot that we can actually manipulate. This is what we truly want with the AI. So even if there is worse performance, we should expect, and stochastic gradient descent generally doesn't find this, then because this is what we actually truly want, we're going to push stochastic gradient descent into making explicit goal slots. So that's why we might have those, even though stochastic gradient descent by default doesn't search for it. It's also claimed that separately trained reusable modules just straight up cause worse performance. I think, like, I haven't looked into the reference much for this. Like, it is my understanding that many of the state-of-the-art models are in fact mixture of expert models, and that seems like at odds with the claim that it just causes worse performance. There's a statement that this is a consequence of the free lunch theorem. Eliezer Yudkowsky has said in a polite way that these theorems are often irrelevant. I'm going to say something substantially stronger. I've never seen a relevant usage of the no free lunch theorem with regards to AI safety. Mostly I think this is an area where reasoning on priors is just silly, because like ChatGPT is totally a thing that exists, and ChatGPT like very obviously has a goal slot, right? You can go into ChatGPT and say and type in pretend to be a paperclip maximizer, and then it has a goal slot that points to something in your prompt, and then it does what a paperclip maximizer would do or something, or it pretends to be an I don't know, a poet or something like that. You can totally point ChatGPT at goals. And so the question, will it be possible to make something like ChatGPT where you can just give it an order and then it does it, is kind of like a silly thing. Like, why should we reason on priors with this when you can just literally go to chat.openai.com and see that it is in fact possible to have an AI that has this kind of goal slot. One of the examples that Nora Belrose used is a medical operation planning system, and if we can talk about the goal of such a system. So let's say you build it in 2 stages. The first is you ask a large language model to give you a number of possible plans for this operation, and then you put this to a classifier that looks at which is less likely to lead to a medical malpractice lawsuit, and then you just pick the plan that scores lowest. Can you say anything about the goal of this system? And the goal becomes much more interesting, both to me and to Belrose, when the AI is more capable. And Nora Belrose chose to increase the power of the system by just increasing the number of possible operation plans. And I think this is a kind of non-intuitive way to make more capable systems. I think it's much more interesting to use an intuitive sense of like the capability of the large language model instead. These two definitions agree when we have either a very low number of possible plans or a stupid large language model. In this case, then we're not really minimizing malpractice lawsuits here. We are trying to make good operation plans. And I think that is, in fact, the correct way to look at this. But now let's assume instead that we get a huge number of operation plans, but all of them are made by a stupid large language model. What probabilities are going to give, we see that will give the lowest probability of a lawsuit? Well, in this case, it's producing a huge number of plans, and almost certainly some of them are adversarial to the classifier. And that means, you know, you have seen these adversarial examples, right? And you will get something that the classifier says has 0 probability of a lawsuit, and then actually it doesn't do operations, and that leads to actual lawsuits. So in this case, the system is not at all characterized as something that minimizes medical malpractice lawsuits. But this is a strange way to think about increasing capability. So let's assume instead that the number of plans given by the large language model is still very small, but the prompt is that give me a plan with the smallest probability of lawsuits, and the large language model is a super intelligence. So it is really, really smart at giving a good prompt for this. What would it then do? Well, probably it would give one that is not merely adversarial to the classifier, but one that tricks the classifier and results in a takeover at the same time, because that is like the best plan. And in this case, the entire system should now be thought of as a lawsuit minimizer, and that will take over the same way as a paperclip maximizer. The next section refers to an argument by Jerry Fodor in What Darwin Got Wrong, and this is held up as an example of that goal realism can lead to absurd conclusions. I would like to point out here, I am confused somewhat about this. Like, this is, as far as I can see, some totally crazy person who has this goal realism, and yeah, he may be totally crazy, but like the non-strawman arguments doesn't really have anything to do with what he says. So I'm somewhat confused, and actually now that I think of it, I'm going to skip through all of it, except with just briefly noting that that humans in fact seem to have goal realism. It seems strongly explanatory to me that I have a goal to achieve something, and then I make plans to go out and do that. I think it feels strongly from the inside like humans do in fact have goals. But I'm not going to talk about this. Let's instead talk about the claim that goal reductionism is powerful, because like it may in fact be that which one is true might not matter so much if one of them is very useful. And the claim is stated here that goal reductionism makes it easy to predict an AI's goal. And I was very happy when I read this, because then perhaps we could figure out, is the AI a schema? Like, that's the thing we're trying to figure out, like what is the actual goal? And when I heard it makes it easy to predict the AI's goal, I was very happy. But unfortunately, a couple of paragraphs later, Nora Belrose admits that it doesn't answer every possible goal-related question. And unfortunately, it seems like in the class of questions it doesn't answer is like, is it a schema? The advantage, again, is that we reduce questions about goals to questions about the behaviors we can see in the training data. And it's really nice to reduce it down there, but also makes it impossible to catch schemas, because you can't see that from the training data. So we reduce it so much that we can't actually answer the question. And this is contrasted with the claim that goal realism leads only to unfalsifiable speculation. And like, there are probably a number of ways to empirically look into this. Joe Carlsmith has a number of those in his paper, but I think like it's always not unfalsifiable in the sense that you might very literally, through mechanistic interpretability, find some nodes in the neural network that you believe this is actually literally the goal slot. So it's not unfalsifiable in this sense. And I think mostly like this is an empirical question. Does a goal slot exist? That is criticized kind of like a philosophical direction. Joe Carlsmith actually puts more credence in his hazy counting argument. There are lots of ways that a model could end up as a schema, so we need some additional story for why the stochastic gradient descent training will not select a schema. And Nora Belrose claims that the overfitting counterexample still holds, because there are lots of ways that a model could end up overfitting. But Joe Carlsmith answers that he thinks he has a story for why neural networks don't overfit, and that is simplicity. And then Nora Belrose counters that actually overfitting could be considered simple. And I notice on the object level that I'm confused. I would have expected that the reason they don't overfit is regularization. So I'm confused at the object level. Again, please don't take my words as gospel here. I may just be confused. But on the meta level, I feel much more confident that a story exists. Like there is actually a good reason why neural networks don't overfit if they have more parameters than data points. And the reason I believe that such an argument exists is like I can look at reality and see this is obviously a thing that happens. So I believe that there is a good story there. There's a reason why neural networks don't overfit, and that doesn't really.
What about grokking?
What about grokking?
I mean, the idea of grokking basically is like describing this entire thing, right? Like, at first you have overfitting with the neural network, and then suddenly at some point it magically stops overfitting because like some subtle like quirks of how SGD works, and then it like suddenly generalizes, and you go from like very bad performance on a test set to very good performance on a test set.
Isn't that deep double descent?
Yeah, that's what I'm referring to.
Right.
I'm somewhat agnostic, in fact, about the precise cause. There could be many stories why this happens. I'm just confident that a story exists. I believe that there is a good argument why neural networks don't overfit in this case. And that is the difference between the two cases. Because with regards to schemas, we can't look at reality. So we don't know if such a story exists. And that's the key difference between overfitting. And like a lot of the stories about like deep double descent and grokking are things that I think would have been really hard to predict in advance when reasoning on priors, and of course schemas that are deliberately hiding their goals would be even harder to figure out just based on priors whether they exist and how likely they are.
I'm sorry for interrupting again,
Sure.
but it seems like this would be the type of thing you can test empirically. Like before we get to the point of superhuman AI, we should encounter schemers. Like we should encounter schemers on a human level, or I guess definitely we should see them. Well, not definitely, but my gut intuition is that we should see them on like a subhuman level too.
So the obvious example of this would be Evan Hubinger's work on sleeper agents, which is doesn't precisely show schemas, but shows things that are pointing towards schemas. And this kind of empirical work is, I think, one of my key points with all this is that this kind of empirical work is in fact much more valuable than trying to reason from more or less informative priors. So I think we agree on this. Okay, let's talk about simplicity, because Joe Carlsmith tries here to investigate a bias argument that goes in the other direction, not just that schemas are more plentiful, but also that stochastic gradient descent is more likely to find those. So this is a stronger claim that is needed for the counting argument. This is that reality is actually biased towards the schemas. And the way he defines symbol is low description length. Nora Belrose objects that now we're just using simplicity as another word for likelihood. I'm somewhat confused about this because, like, if you say they are more likely, then we have already established that the counter argument probably works. But Nora Belrose claims that we can't appeal to our intuitive notions of simplicity to conclude that one hypothesis would truly be simpler and hence more likely. And I think in general we can do that. In fact, it is like there are some things that are obviously simpler than others, in particular if we are talking about something that seems strongly complex, like an entire description of human values is more complex than a bit that is like one. I think this is the kind of things we do have some level of intuitions about. And finally, Nora Belrose claims that this idea of scheming is inspired by Christiano's work on the universal prior. As far as I could see, Joe Carlsmith's work is not very inspired of this. He mentioned it in a footnote where he calls it like really speculative discussions, but it seems very clear to me that Joe Carlsmith's arguments are not based on the work on the universal prior. That is all for today. Thank you and see you next time.